always been fascinated by this picture. It's a mural in Confucius' home in East China. And the magic point of this photo is that no matter which direction you look at it, like what position you stand in front of it, you always feel that this road is straightly pointing forward. And so they gave it a name called the Sunny Way. And so this mural continues to attract people's attention even after hundreds of years. Well, in reality, the normal design life of a street is only about 30 or 40 years, at the end of which cracks and ruts start to appear, and potholes start to pop up. So it's something like Abbey Road here. Or this beautiful poster scene with cracks at the behind. And this is another example of pavement degradation. These are two different roads in the city of San Francisco, and we can obviously see that the one on the top has a much better condition. And now, what if that I tell you that these two roads, they have almost the same condition 20 years ago, and road X has better condition only because it was maintained twice. And so I think this highlights the importance of doing maintenance of pavements. But pavement maintenance is both a science and an art. It's a science because it's based on many numbers, especially for large-scale things like the allocations of maintenance budget, and reporting. However, if we come to localized pavement maintenance like pothole filling, it's pretty ad hoc. And so not being able to find the optimum time of patching the potholes or seal the cracks is a major cost factor in why it is so expensive. So naturally we think, can we do something to improve the the knowledge in localized pavement degradation so that we can have a better understanding of how it behaves and when to repair it. Luckily for San Francisco, we not only have records of these two streets, we have the records of the whole city for 20 years. And here I show the snapshot of the condition of the road in 4 different years. And the condition is summarized by an index called the Pavement Condition Index. It was invented in the US about in 1980s, and now is widely used in the world. We don't have a record for each street at every year, but most of the time the gap between the observations is 3 years or 4 years. So we want to find out what is causing road degradation. We draw this parallel coordinate plot that I learned in the master class when I came to the ATI. And so the first coordinate here represents different road degradation rates. And the faster it degrades, the lighter the color. And then on the other coordinates are different kind of factors that we think will affect pavement degradation rates, including traffic and cars traffic and heavy traffic, and the road gradient, road type, area type, and functional class. But none of them seem to be able to separate this degradation trend easily. But still, we were able to find 2 factors that we think are important. The first one is time. For example, here is a plot of all the observations. The y-axis is the pavement condition index, and the x-axis is the age since last maintenance. As we can see, as time goes on, the condition drops, even though it's very random. And different colors here represent different road class or different surface type. And these 2 factors, though we think they are important, cannot really separate different degradation behaviors. And another thing that we find seems to be able to help us in understanding degradation is the conditions of the neighboring street. For example, if the condition of one street is not very good, then very likely its neighborhood is also not in a good condition. And this is not counterintuitive because neighboring roads tend to be maintained together and constructed by the same team, so they will have more similar degradation behaviors. So we think whether it is possible to incorporate this spatial and temporal dimension into road degradation modeling on a street level. Usually, spatial modeling is very slow, so to be able to do tests at a fast speed, I only select one area out of the city, the Sunset District. I choose this area because it's mostly residential, so the traffic is more homogeneous, and also because it has very regular grid network that I can define neighbors easily. And here it shows the correlation, the spatial autocorrelation between neighboring rows. And the x-axis is the spatial lag. If the two pavements, they are next to each other, then they are first-order neighbors. And the first-order neighbor is the second-order neighbor. So as the order of the spatial lag increase, the correlation between the pavement condition 5 years after maintenance drops. So there seems to be something that we can borrow strength from the neighbors to improve our predicting ability. Oh. Okay, so this is the a degradation model. It's a latent Gaussian model, but actually it's very simple. So on the top layer, this is my road condition, and I assume it's sampled from a Gaussian distribution. This is also reasonable because pavements is usually surveyed by some vehicles or the trained personnel, and they have some survey accuracy, but they all centered around the true value. And then I assume the true value is a area-specific variable, and is a linear combination of many factors. For example, the pavement age, or the spatial factors. Then I designed these two categories of models. The first one with the red background is the non-spatial model. For the one on the top, basically I just fit one line to all the degradation records and to see if pavement condition can just be predicted by the age. And then this one is that I allow different streets to have different intercepts. So I'm fitting a series of parallel lines. Why I'm doing this is because the road maintenance not always restores the condition to 100 or to the same value. So, but most of the time, the same road, they begin at the same condition. So I allow it to vary by different roads. And then the third one is to allow them to have different degradation rates, because they may start at the same condition, but because of the traffic and some other factors, they may degrade at different rates. And the last one is just to fit a line to each model. And the one on the one column here are spatial models. They are basically very similar to the non-spatial models, but instead of letting this parameter, for example, the intercept, which represent the age 0 condition, to vary individually by each street, I assign a spatial constraint to it so that the age 0 condition is represented by a global average alpha and the individual residue called cosine I. And cosine I is related to its neighbors j by imposing the constraint that the mean value of its neighborhood is the mean value of cosine I, and it has the variance also related to the number of neighbors it has. If you have more neighbors, then I'm more certain that you will be taking this value. And because of the time, so maybe I will just go through the results of the these two models. And for the non-spatial models, I use the parameter estimation using the frequentist ordinary least squares, and also a new method called INLA, which I will introduce later. And for the spatial models, I use the inference method INLA and the MCMC. So this is the integrated nested Laplace approximation. It is one way of doing Bayesian inference, and I choose it not because I'm a fan of Bayes' method or I'm a fan of this, but because this method is very convenient for modeling spatial problems. It has several models built in, and it is very fast. So basically, the first line is the posterior of the parameters and hyperparameters. It can be expanded according to the Bayes theorem. And what we are interested in are the marginal posteriors of the different parameters. For example, the degradation rates or the H0 conditions, they are all represented as this value. And the hyperparameters, we also want to know them, such like what is our precision about these distributions. And these are just conditional distributions. And then the use of these two lines is to bring this problem to a much lower dimension so that we can do integration on a much lower dimension, which equals to the dimension of hyperparameters, which is usually much lower than the number of parameters. And next, we want to know the integrants. And we can write it out also based on conditional distribution. And the first, the numerator is just the posterior distribution. And the denominator, we use the Gaussian approximation. And so like all the values here, we can express them out, and then we can do numerical integration. And that's also the reason why it's so fast. OK, now let's see the results, especially how it compares with more traditional methods. So first is the non-spatial model. I basically get similar results, like almost the same results from the maximum likelihood estimation, the frequentist method, and INLA, and INLA's posterior estimation. And it shows that the degradation rate for the roads in San Francisco is about 2 per year. So if it starts at 100, and we take like 60 as a condition that it needs to be repaired, so it's possibly after about 20 years. It's a bit slow, but possibly because I have some errors in the data. And about the 8-0 condition, if you call it in a panel data analysis way, it's the fixed effects. So I shouldn't really report the mean and the standard deviation. But because I have 800 of them, so I cannot report them individually. So I just report the mean. So most of the streets, they start as a condition about 90, and the standard deviation is 7.76. And this is an illustration of model 1. And then for the spatial model, I used INLA method to get my estimations of the parameters and also the MCMC. And the results are also very similar, but I cannot really believe it because the MCMC is so fast. So that is contradictory to what I have been told in the papers, and I'm still trying to think why. And look at the posterior distributions of the parameters. They also look pretty similar to the INLA one. So in this sense, I'm not sure if INLA is really better than MCMC maybe in this specific setting. And here are some plots of the results. For the non-spatial model, this map shows the starting condition of all the streets. And you can see the distribution is pretty random. But comparatively, the one for the spatial model, it is more uniform. And so maybe we can think that in the future, if we don't have enough data, we can really borrow strengths from the neighbor and to use them to fit one model. And I'm saying this because both of the two models, they achieved comparable accuracy in fitting the data. And the information criteria even suggests that we want to choose the spatial model because it has less effective numbers of parameters. And here's the reason why we do spatial modeling. It's because that if we don't do this by just using a simple model of alpha plus beta times t, then we'll have a very big autocorrelation in the results, and that's usually what we want to avoid in regression. However, using spatial models, the autocorrelation is much lower. Using non-spatial models, the autocorrelation is also lower, but that's on the price of using much more parameters. So looking forward, this shows the all the road works, utility works that's going to happen, already happening around us in the next 2 months. But when we want to look for the future, this is one of the things that we want to consider. So how to schedule maintenance, including roadworks and utilities, and to minimize the traffic disruption. So when you drive on the road, it would happen again that all the turnings are blocked because they are doing maintenance altogether. And there are some other things we want to look into in the future, such like getting some more real-time condition reporting of the pavement condition, like using accelerometer data from the smartphones of the driver or satellite imagery. And I've tried the second one before, but it doesn't work at this time because all I can see are the cars on the street, not potholes. And we also want to explore some possibility, possibly a bit in the future. It's like if we can guide vehicles to travel on smoother and better conditioned roads, but not just the shortest distance. This is not only good for the drivers, for the cars, but also good for the roads, because usually the roads degrade exponentially. And when they're already in a bad condition, we should protect them, not to use them more. And I've seen research saying that people would like to spend more time to take a route that goes through a park. So I guess people would possibly like to do it if they are provided with enough incentives. And then the last one is to calculate the fuel consumption and gas emission in different scenarios, not only based on traffic, but also based on road condition. Because the more bumpy the road is, usually the emission and fuel consumption is also higher. So here's my summary. We now know that the effective maintenance is very important for managing the existing pavements. But how do we make effective maintenance? Understanding degradation is really important. And we built on some open road condition data, a spatial explicit model. And we find that it can achieve comparable performance in terms of predicting accuracy, but with a smaller effective numbers of parameters. And in the future, maybe we need to design more careful spatial models that can even do better than this. And the analytical approximation-based INLA method is compared to the frequentist and also the MCMC to estimate parameters. And in that specific case, all of them, they seem to be agree with each other really well, but not in the other models that I don't have time to show yet. But the difference we can explain. And the last one is that at this moment, the models do not fit or predict well, which I agree, because if we consider a fitting error of 10 out of 100, then it's quite big. Honestly, if we talk about the future, in order to better manage our payments, should we have more data or have more complex models, or maybe just to use a different way of thinking instead of trying to predict, which is unpredictable? Can we do better maintenance based on the real-time condition and try to find the problem as early as possible instead of trying to predict it? Okay, that's all. Thank you.